Alright, Unit 11. Oh, jumped the gun. Unit 10, waves. So we get in here to Unit 10, start defining a couple points on the wave. First of all, the top is called the crest, but remember it can also be called something else. It can also be called the antinode. Let's put AN for short. This is called the amplitude, the difference between the node and the antinode, or the x-axis to the peak or trough. This is called the node, or the point where the wave crosses the x-axis, and this is called has two names. It can be called a trough, but it can also be called an antinode. Again, that happened up here, don't forget. Frequency is 1 over the period, so T goes down here. Remember, this is designed for the person who is not going to use their formula sheet. Units being hertz or 1 over S, same thing. Spring constant, 2 pi quantity squared, 39.5. Don't forget to make it a quantity, otherwise you end up with 4 times pi, which you don't want. And then we have the period squared on the bottom. Units are newtons over meter for spring constant. Velocity, frequency times wavelength. It can also be found by taking the spring constant times the amplitude squared divided by the mass, square root the entire thing. Now, the thing about this is the speed of the wave here, and this is the speed of the object vertically. This will be the horizontal speed of the wave. So keep that in mind when you go through and do this. Come over here and do the example now. Looks like we have a distance of 4 centimeters between trough and crest. That makes the amplitude in meters equal to 0.02 because it went from trough to crest. The period, time it takes to go from the bottom back to the bottom, would be 1.6. And the frequency then would be 1 over 1.6, which is 0.625. And the wavelength, I didn't tell you the distance between crests or troughs, so I'll just put an X in there because we don't know it. Which means that this velocity that we're solving for here has to be the velocity of the object in the y. So that kind of eliminates some of that. So we'll use, first we got to find k, because you can't find the v and the y without how stretchy or how elastic the media is that it travels in. So we find the spring constant. Even though there's not a spring in this problem, water itself has a spring constant. So 39.5, 2 pi squared times the mass. The mass was 0.004, as 4 grams are not a lot of mass. Then we divide by the, the period squared, so that was 1.6 squared. And we can get k. So when we do that, we find the k is 0.062. I would just probably type it in like this. I would probably just skip all this quantity business and just go 39.5 times 0.004 divided by 1.6 squared. You can see it's 0.062. Once you have k, then we can use the other relationship, which is the y velocity, which is square root of k times a squared divided by m. So that's going to be our previous answer, 0.062 times the amplitude, which was 0.02, divided by the mass, which was 0.004, and we square root all of that to get the y speed. Remember, we did this in lab not too terribly long ago. So we take our previous answer times 0.2, divide by the mass, and we square root it, and we get 0.555 as our velocity. That's the y velocity. The velocity going the other way can be found by taking frequency times wavelength. So this would be the y velocity, 0.555 meters per second. Hang on to that number. Now let's review how we find the velocity of the wave, frequency times wavelength, which we know both. The frequency was 0.625 and the wavelength we didn't have enough given, so we can't really solve for that. But that's kind of how it works for this problem. So, point being, I just want to check this one more time. Oh, whatever, I'll check it on my own time. Alright, on to the next one.